Hello everyone and welcome back to your YouTube channel and welcome to this lovely video today. As you must be aware, I am recording this series of videos related to electromechanical conversion systems. And one of the amazing conversion systems that you can think about is the DC generator. So today the job is to solve a numerical example related to a shunt DC generator, and in this very specific case what we are doing is using the circuit model of this DC generator to calculate electrical variables. So without further delay, let's start by reading this interesting statement. A shunt DC generator supplies a load, 30 kilowatts load at 300 volt through cables. So the very interesting part over here is that these 30 kilowatts and these 300 volts are basically located here, and that is the load of this DC generator. However, this load is connected by cables to the DC shunt generator. The resistance of the cables is 50 milliohms. And if the field winding resistance is 50 ohms and the armature resistance is 40 milliohms, determine first the load current in amps, the voltage drop in the cable in volts, the terminal voltage in volts, the field winding current in amps, the armature current in amps, the EMF generated in the armature in volts, and finally the mechanical input power at the DC shunt generator. So what is important for you is that we include over here the circuit model of the DC generator and this very interesting load condition. As you can see on the right hand side, we have the classical model of a shunt generator. You can identify between labels A1 and A2. This is the armature circuit that is connected in parallel between F1 and F2 to the field winding. But what is interesting for this very specific case is that we have a resistive load over here, 30 kilowatts, and we know that the terminal voltage is 300 volts. But what is extremely important for my student to understand is the use of cable to connect the DC generator to the load. As you can see, there is a cable starting from the positive terminal of the generator and going to the positive terminal of the load. And same situation happened on the negative side. We have here a cable that is connecting the negative terminal of this DC generator to the load. So that is very important because you need to understand that in this circuit you need to use two cables, and that means two resistance. So, as you can see today, I am using this MATLAB Live script, one of my favorite tools for solving problems, numerical problems, because also allow me the integration of these useful diagrams, also equations, and tests to explain the solution. So over here, the first part of this script over here is basically the data that we know. We know the demand at the load, 30 kilowatts. We know the terminal voltage at the load, that is 300. We know the resistance of the cable, the field winding, and also the armature. Now what I will do is just basically include here references for the voltage drop across the cable. And what I will do is I will apply all my knowledge about circuit analysis in this very specific circuit where we are connecting the DC generator to the load. So the first question is related with the load current, and the load current is very simple to be calculated because we already know the load power, and in this case is 30,000 watts, and we know the terminal voltage, and the low voltage, and that is 300 volts. So we divide the 30,000 watts by 300 volts, and we obtain here, you can see this is the current, this is the low current, that is 100 amps. Now what I will do is calculate the voltage drop across one of those cables, and for do that, what we need to do is just basically use Ohm's law. And Ohm's law say that the resistance multiplied by the current, it will be the voltage drop across this cable. So in this case, we know that the cable is 50 milliohms multiplied by 100 amps that we already calculate in the previous question. And we obtain that the voltage drop across this cable over here is 5 volts. But remember, we have two cables, so the total voltage drop through the connection system will be 10 volts. But now what I want to do is to calculate the terminal voltage over here, and to do so I can use Kirchhoff voltage law on the left-hand side of the circuit. In other words, what I am telling you is that Kirchhoff voltage law will tell me that the terminal voltage is twice the voltage drop through the cable plus the voltage at the load. That is 300 plus 2 multiplied by 5 volts. So the terminal voltage in this case is 310 volts. So next step is the field winding, and the field winding current is this current over here. Is very simple to calculate because we already know that the terminal voltage is 310 volts. So what we need to do is apply Ohm's law, dividing 310 by the field winding resistance, in this case is 50 ohms. So as you can see over here, the result is 6.2 amps. The next step is we want to know the armature current, and to get the armature current, to calculate the armature current, what we need to do is apply Kirchhoff current law here at the top. And as you can see here, the armature current should be the terminal plus the field winding. And that is what I draw here. You can see that the field winding current is 6.2, terminal current is 100. So adding those currents, we obtain the armature current, and for this very specific case, 106.2 amps. The next step is to calculate the induced electromotive force over here, or EMF. And to do that, we can just use Kirchhoff voltage law through the terminals A1 or A2, and that is basically the armature. And over here, you can see the Kirchhoff voltage law. You can see that the armature voltage will be the terminal voltage plus the voltage drop through the armature resistance. So that will be 106.2 amps multiplying the armature resistance 40 milliohms and adding the terminal voltage 310. So as you can see, the armature voltage, it will be 314.2 volts. And finally, to conclude this very exciting problem, we want to calculate here the input power. And everyone remember from the theory, everyone remember from my classes, that the input power, if we neglect the losses related to friction and any other losses in the conversion from mechanical to electrical, well, you must remember that in that case, if the efficiency is 100%, the mechanical input power should be equal to the power dissipated by the MMF. And in that case will be the armature voltage multiplied by the armature current. And that is the equation that you can see over here. The mechanical input will be the voltage dissipated by the mmf. So multiplying 314.2 volts by the armature currents 106.2, we obtain the mechanical power, and in this case the mechanical power will be 33,375.1 watts. What is interesting to see over here is that we need more mechanical power. You can see that this could be 33.3 kilowatts just to deliver 30 kilowatts to the load. And the reason that we need more mechanical power than the load here is because we have several resistors over here representing the copper losses through the windings and the cable. So as expected, the input power will be larger than the load. So this is the final result over here. This is the mechanical output, the mechanical input, and that is 33.3 kilowatts. So we reached the very end of this exciting video, and today we study the operation of the DC shunt generator by using the circuit analyzer and apply to the circuit model of the DC generator. And this has been a very exciting demonstrative example of using MATLAB Live Script to teach you how to use the tool for calculations. Well, sadly, this is the end of this video. I would like to say thank you very much for watching the video. I hope that you understand the explanation, you enjoy the video and the full explanation that I did here for you. And if you want to keep the track about what we are doing, I highly suggest to subscribe to our community. As you can see over here, there are links for the LinkedIn profile, the YouTube channel, Twitter, and Instagram. So this is the end for this video, and thank you very much for watching, and I need to say bye now.